In 1991, deep inside a classified facility, a team of American engineers watched their creation come to life for the first time. The particle bed reactor held together. The system worked. For a brief, electrifying moment, they had done it. They'd built a rocket engine that could revolutionize spaceflight, reaching Mars in a fraction of the time of any chemical rocket. But, as one technician would later recall, seeing the system hold together was like watching a miracle unfold. What they didn't say out loud was what they were all thinking. They'd also created something that could spread radioactive contamination across entire continents if it failed. This is the story of Project Timberwind, the most powerful rocket engine ever built, and the dark secret of why it was buried before it ever flew. To understand why Timberwind mattered, you first need to understand the prison that has confined spaceflight since the very beginning. It's called the rocket equation, and it's as beautiful as it is cruel. The mathematics are elegant, simple even, but their implications are devastating. Every kilogram of payload you want to carry requires fuel, but that fuel has mass, which means you need more fuel to carry the fuel. And that additional fuel has mass, requiring even more fuel. It's an exponential spiral, a tyranny of diminishing returns, that has haunted every rocket engineer who ever lived. Chemical rockets, the kind we've relied on since the dawn of the space age, face a hard physical limit. They work by burning fuel and oxidizer, creating hot gases that rush out the back, pushing the rocket forward. The hotter those gases, the faster they move, and the more efficient your rocket becomes. We measure this efficiency with something called specific impulse. Essentially, how many seconds a rocket can produce thrust from a given amount of propellant. It's the miles per gallon of spaceflight. And here's the problem. Chemical rockets, no matter how cleverly designed, max out around 450 seconds of specific impulse. That's it. That's the ceiling. The chemistry simply won't allow anything higher. This limitation isn't just academic. It defines what's possible in space exploration. With chemical propulsion, a mission to Mars takes 8 to 9 months of transit time. That means 8 to 9 months of life support, radiation exposure, bone loss, and psychological strain for any crew. It means massive spacecraft to carry all the supplies needed for that journey. It means launch windows that only open every 2 years when Earth and Mars align favorably. The rocket equation doesn't just make Mars missions difficult, it makes them almost prohibitively expensive and dangerous. But what if you could shatter that ceiling? What if, instead of chemical combustion, you used a nuclear reactor to heat your propellant? Nuclear reactions release millions of times more energy than chemical reactions. In theory, you could heat hydrogen propellant to temperatures that chemical combustion could never achieve, producing exhaust velocities that would make chemical rockets look like horse-drawn carriages next to a supersonic jet. This was the promise of nuclear thermal propulsion, and it had captivated a small community of physicists and engineers for decades. Among them was Dr. George Miley, a pioneering nuclear physicist, whose fascination with atomic power had driven him to believe that nuclear propulsion was humanity's only realistic path to the stars. For Miley, this wasn't just about engineering specifications, it was about vindication. He'd spent decades championing nuclear technology for peaceful purposes, watching public fear and political resistance repeatedly thwart promising applications. Nuclear thermal propulsion represented a chance to prove that atomic energy could be more than weapons and accidents, that it could be the key that unlocked the solar system. The concept was straightforward enough. Build a nuclear reactor, pump hydrogen propellant through it, let the reactor heat the hydrogen to extreme temperatures, and exhaust it through a nozzle. Early nuclear thermal concepts promised specific impulses of 800 to 900 seconds, nearly double what chemical rockets could achieve. Run the numbers, and suddenly Mars missions could be measured in weeks rather than months, 6 to 8 weeks potentially, instead of 8 to 9 months. The implications were staggering. Shorter missions meant less radiation exposure, less life support mass, smaller spacecraft, lower costs, and dramatically reduced crew health risks. This wasn't idle speculation. NASA had actually built and tested nuclear rocket engines in the 1960s and early 1970s under a program called NERVA, Nuclear Engine for Rocket Vehicle Application. They worked, they produced the promised performance, but they had one fatal flaw. They were heavy, incredibly, prohibitively heavy. The problem was fundamental to the design. Nerva-style engines use solid fuel elements, essentially rods of uranium arranged in a reactor core. The hydrogen propellant flowed through channels in these fuel rods, absorbing heat. But solid fuel rods required massive structural support to prevent them from vibrating apart in the intense flow. They needed heavy radiation shielding to protect nearby components. They needed thick pressure vessels and elaborate cooling systems. When you added it all up, yes, you got better specific impulse than chemical rockets, but the engine itself weighed so much that the overall performance advantage largely evaporated. If your nuclear engine weighs 3 times more than a chemical engine, but only provides twice the efficiency, you haven't actually gained much. This was the wall that nuclear propulsion had hit. The challenge wasn't just making a nuclear rocket. It was making one light enough to actually provide a meaningful advantage. For years, it seemed like an intractable problem. The very nature of nuclear reactors, the shielding, the structure, the safety systems, seemed to demand mass that negated the performance benefits. And that's where Dr. Leonard Wood entered the story, with an idea so radical, so counterintuitive, that it would either revolutionize spaceflight or fail spectacularly. Wood was a rocket engineer with a reputation for relentless optimism and engineering brilliance. Where others saw intractable problems, Wood saw opportunities for radical rethinking. He looked at the Nerva design and asked a simple question: what if we got rid of the solid fuel rods entirely? His alternative was audacious. Instead of solid fuel elements requiring heavy structural support, what if you used thousands of tiny fuel particles, each smaller than a grain of sand, suspended in the flowing hydrogen propellant itself? The propellant flow would keep the particles suspended and separated, eliminating the need for structural supports. The particles would have enormous surface area relative to their volume, allowing for much more efficient heat transfer. And because the particles were small and could withstand higher temperatures without melting, you could run the reactor much hotter than solid fuel elements would allow. Wood described it as a fluidized bed coffee percolator. Imagine coffee grounds suspended and agitated by boiling water, dancing in the turbulent flow. Now, imagine those coffee grounds are actually tiny spheres of uranium fuel, and the water is hydrogen moving at supersonic speeds, being heated to temperatures that would vaporize steel in seconds. That was the particle bed reactor concept. The advantages were compelling. The dramatically increased surface area meant better heat transfer. You could extract more energy from the nuclear reaction and dump it into the propellant more efficiently. The elimination of heavy structural supports meant a much lighter engine, and the ability to operate at higher temperatures meant higher performance. Timberwind's particle bed reactor was designed to achieve a specific impulse of 900 to 1,000 seconds, more than twice the efficiency of contemporary chemical rockets. But the real breakthrough was in the thrust-to-weight ratio, how much thrust an engine produces relative to its own weight. This is critical, because a heavy engine eats into your payload capacity. Nerva-style engines achieved thrust-to-weight ratios of 3.1 or 4.1, decent, but not spectacular. Wood believed Timberwind could achieve ratios of 15.1 or higher. That would approach the performance of chemical rockets while maintaining the efficiency advantages of nuclear propulsion. It was, potentially, the best of both worlds. The concept was brilliant on paper, but it introduced a terrifying new variable. Those thousands of tiny fuel particles had to remain perfectly suspended in supersonic flow. The physics was delicate, dependent on precise flow velocities and turbulence patterns. If the flow became unstable, if particles began to clump together or settle in one region of the reactor, you could get localized hotspots. Fuel particles could melt. They could agglomerate into larger masses. They could escape the reactor entirely, and every one of those particles was radioactive. A catastrophic failure of flow stability didn't just mean engine failure, it meant potential release of radioactive material. But Wood was convinced the physics would work. The question was whether he could convince anyone else, particularly the people who controlled the funding, and as it happened, the timing couldn't have been more perfect. In the mid-1980s, the Strategic Defense Initiative, popularly known as Star Wars, was consuming billions of dollars in pursuit of an ambitious goal: developing space-based weapons systems capable of intercepting Soviet nuclear missiles. The concept required spacecraft that could maneuver rapidly in orbit, changing trajectories quickly to intercept incoming warheads. Chemical rockets couldn't provide the necessary performance. They couldn't deliver the delta V, the change in velocity needed for the kind of aggressive orbital maneuvering the mission required. Nuclear thermal propulsion was identified as a key enabling technology, and Wood's particle bed reactor concept, with its promise of high thrust-to-weight ratios and excellent specific impulse, looked like exactly what SDI needed. Around 1987, Project Timberwind was born as a black budget program under the Strategic Defense Initiative Office, with funding and oversight from the Air Force and Department of Energy. It was classified from the beginning. Compartmentalized research, need-to-know restrictions, facilities within facilities. The team drew researchers from national laboratories including Los Alamos and Brookhaven, aerospace contractors, and military liaisons. They worked under extreme pressure and intense secrecy, surrounded by security protocols and the constant presence of armed guards. For Miley, Wood, and the rest of the team, the secrecy was both thrilling and isolating. For the first time, we felt we could actually build a rocket engine that would change the future of spaceflight, Dr. George Miley would later recall. The sense of urgency and secrecy only heightened our commitment. They were working on technology that could genuinely transform humanity's relationship with space, but they couldn't tell anyone about it. There was a profound irony in the arrangement. A project designed to enable weapon systems was also humanity's best shot at efficient deep space propulsion. The same engine that could power a missile interceptor could also power a Mars mission. Military funding was making possible what civilian space agencies had been unable or unwilling to pursue. But that military connection would later become a liability. Secrecy came with a price. The very classification that protected Timberwind also isolated it from the broader scientific community. Peer review was limited to those with the appropriate clearances. Independent safety analysis was restricted. And most critically, the public, whose support would ultimately be necessary for any nuclear rocket program, had no idea this technology even existed. The team was building something revolutionary in a bubble, cut off from the normal mechanisms of scientific discourse and public accountability. While the world remained oblivious inside those classified facilities, the team was about to face their first major test, proving that particles could actually stay suspended at the temperatures and flow rates required. The engineering challenges were formidable. First, there was the materials problem. You needed fuel particles that could withstand temperatures exceeding 3,000 Kelvin, hot enough to melt most metals, while maintaining structural integrity and not reacting chemically with hydrogen. The particles needed specialized coatings, carefully engineered compositions, and manufacturing precision measured in microns. Then there was the flow dynamics problem. Achieving the precise velocity and turbulence needed to keep particles suspended without creating destructive vibrations or pressure oscillations required sophisticated understanding of fluid mechanics at extreme conditions. The mathematics were complex, the experimental validation even more so. Early tests revealed problems no one had anticipated. Flow instabilities caused particles to migrate to certain regions of the reactor. Unexpected erosion patterns appeared. Pressure oscillations threatened to tear components apart. And always, lurking behind every test, was the threat of fuel particle escape, radioactive material breaching containment. The team adopted an incremental approach, building confidence through hundreds of smaller tests. They started with non-nuclear simulant particles, gradually increasing temperatures and flow rates. They developed novel injector designs to create the right flow patterns. They built real-time monitoring systems using advanced sensors that could track particle behavior inside the reactor during operation. They designed test stands with remote operation capabilities and extensive radiation monitoring, with emergency shutdown systems that could kill the reactor in milliseconds if parameters went out of bounds. The psychological toll was significant. These were engineers and scientists working with systems that could fail catastrophically. Every test carried the awareness of radiation exposure risks, the pressure of the classified environment, the inability to discuss their work with colleagues outside the program, the constant security scrutiny added another layer of stress. And then came 1991. In a series of critical tests, the particle bed reactor prototype held together under conditions approaching operational parameters. The fuel particles remained suspended, the flow stayed stable, the heat transfer performed as predicted. The system worked. Seeing the system hold together was like watching a miracle unfold, one technician observed. It was a moment of triumph, proof that Wood's radical concept wasn't just theoretical speculation, but actual functioning hardware. They had done something no one else had achieved. They had built a particle bed reactor that operated at nuclear thermal propulsion conditions. But that relief was tinged with something else, a growing realization of what they'd actually created. Because proving the concept worked in a test stand was one thing. Actually flying, it was something else entirely. They had to confront an uncomfortable question. What happens when you try to launch this thing? Any nuclear rocket must be launched on a chemical rocket first. There's no other way to get it off the ground. That means a fully fueled nuclear reactor containing substantial amounts of enriched uranium, sitting atop tons of explosive chemical propellant during the most dangerous phase of flight. Launch is when most rocket failures occur. The stresses are enormous. The systems are pushed to their limits. And the consequences of failure are immediate and catastrophic. The team began systematically analyzing the failure scenarios. A launch pad explosion would scatter radioactive fuel across the launch site and downwind areas. An in-flight breakup would distribute contamination along the trajectory. A failed orbital insertion could cause uncontrolled re-entry, with the reactor burning up in the atmosphere and spreading material across a wide area. Even with fuel particles designed to survive re-entry intact, encased in protective coatings meant to withstand the heat, a catastrophic failure could spread detectable radioactive material across thousands of square miles. The contamination might not be lethal in most areas, but it would be measurable, persistent, and politically explosive. Then there was the activation problem. Once a nuclear reactor operates, even briefly, neutron radiation activates the materials in the reactor structure itself. The engine becomes intensely radioactive, not just the fuel, but the metal components, the plumbing, everything. That radioactivity persists for decades. A spent Timberwind engine would be a permanent piece of radioactive space debris, too hot to safely approach or dispose of. And even during normal operations, the engine would vent small amounts of radioactive hydrogen. The quantities might be tiny, the radiation doses negligible compared to natural background. But the optics were terrible. You'd be deliberately releasing radioactive material into the environment as part of routine operations. There was precedent for concern. The Soviet Union had flown nuclear-powered satellites, and in 1978, one of them, Cosmos 954, had malfunctioned and re-entered over northern Canada, scattering radioactive debris across a wide area. The cleanup operation was expensive and politically damaging. The incident had heightened international sensitivity about nuclear materials in space. The regulatory landscape was equally daunting. No framework existed for licensing nuclear rocket launches. Public acceptance was uncertain at best. International treaties restricted certain uses of nuclear materials in space. The team was navigating uncharted territory, both technically and politically. They began running probabilistic risk assessments, statistical models of every possible failure mode, weighted by likelihood and consequence. The numbers were sobering. Even with multiple redundant safety systems, even with the most conservative operational procedures, the probability of some radioactive release during a launch campaign involving multiple flights was not negligible. The question became impossible to avoid. How much risk is acceptable? How many potential deaths per mission can you justify? 1, 10, 0? And who gets to make that decision? The engineers who built the system, the military officers who wanted to use it, the politicians who funded it, or the public who would bear the consequences. Dr. Miley, the nuclear physicist who had championed this technology for decades, found himself confronting doubts he'd never expected. He understood radiation risks intellectually. It was his field of expertise. But there's a difference between academic understanding and practical responsibility. The dream of nuclear spaceflight, which had driven his career, was now forcing him to grapple with questions that had no easy answers. And then, just as these questions were becoming impossible to ignore, the world shifted beneath them. literally overnight. November 1989. The Berlin Wall fell. December 1991. The Soviet Union formally dissolved. The Cold War enemy that had justified the Strategic Defense Initiative simply ceased to exist. The geopolitical context that had birthed Timberwind evaporated. The impact was immediate. SDI funding was slashed. Priorities shifted from space-based weapons to more terrestrial concerns. Nuclear programs, already politically sensitive, became toxic. The peace dividend meant cutting defense spending, and expensive exotic programs like Timberwind were easy targets. For Dr. Wood, it was crushing. His life's work, the revolutionary engine that could change spaceflight forever, was suddenly irrelevant. He tried to pivot, to find new justifications in a world that no longer feared Soviet missiles. Mars missions, he argued. Deep space exploration. Scientific advancement. But without the military urgency, without the existential threat of the Cold War, the political will evaporated. The budget reality was stark. Timberwind would require hundreds of millions more dollars to reach flight-ready status. In the new political environment, that funding wasn't coming. The project limped along for a while, sustained by bureaucratic momentum and the hopes of true believers. But the trajectory was clear. By the mid-1990s, Project Timberwind was effectively dead, buried under classification and bureaucratic indifference. The particle bed reactor that had held together in those triumphant 1991 tests would never fly. The revolutionary propulsion system that could have cut Mars transit times from months to weeks would never leave the test stand. The technology that represented decades of work and billions of dollars in investment was locked away, classified, largely forgotten. Today, the basic physics that made Timberwind promising hasn't changed. The rocket equation still imposes its tyranny on chemical propulsion. Mars is still 8 to 9 months away. Nuclear thermal propulsion would still offer dramatic advantages for deep space missions. But the political, environmental, and safety concerns that helped kill Timberwind remain unresolved. We're left with a profound question. Was Timberwind a tragedy of lost potential, or a cautionary tale of technology that was too dangerous to use? Were the engineers who built it visionaries whose work was cut short by political expedience? Or were they brilliant people who created something that should never have been flown? Perhaps the answer is both. The technical achievement was real. They did solve problems that had stymied nuclear propulsion for decades. The particle bed reactor concept was genuinely innovative, but the safety concerns were also real. The risks weren't hypothetical. They were inherent in the technology itself. Project Timberwind remains classified to this day. Its full technical details still locked behind security restrictions. The engineers and scientists who worked on it are aging, taking their knowledge and experiences with them. The test hardware has been dismantled or sits in storage, radioactive and untouchable. But the dream hasn't died entirely. Interest in nuclear thermal propulsion persists. NASA and private companies continue to study the concept. New designs, new safety systems, and new political contexts may eventually make nuclear rockets viable. Perhaps future engineers will rediscover Timberwind's innovations, learning from both its successes and its failures. For now, though, Timberwind stands as a monument to a particular moment in history, when brilliant scientists built something extraordinary and terrifying, when the pursuit of unprecedented power forced a reckoning with consequence, and when humanity chose, perhaps wisely, to leave that power unused. The particle bed reactor held together. The system worked. But sometimes, the most important question isn't whether we can build something, but whether we should. If you enjoyed this story, hit subscribe for more stories where history, technology, and human ambition collide. Thanks for watching.